Up until now, most of our concentration has been on solid objects in motion or in equilibrium. Fluids are also subject to applications of conservation of energy and momentum, and forces can be applied to them, both in open and closed situations. Chapter 9 covers much of this, addressing the competency solve simple fluid problems. These would include application in closed fluid situations, whether liquids or gases, such as applying Pascal's principle or Archimedes' principle to confined fluids. In these cases, the application of forces is explored. In the case of moving fluids, Bernoulli's principle and the concept of rate of flow can be used. The rate of flow equation combines the cross-sectional area A of a fluid, for example, fluid flowing through a pipe or a riverbed, and the velocity v of the flow at that point where the cross-sectional area is measured. So rate of flow is equal to v times a, and is constant at different locations along the flow path. So one can set the flow rate expression at one point in the path equal to the flow rate expression at a second point, much as we use conservation momentum before and after an event. Knowing three of the items in this expression then allows you to get the fourth. Bernoulli's principle is effectively the conservation of energy applied to moving fluids. More specifically, if one considers the units, the energy per volume of moving fluid is considered. For problems we will be doing, we consider only a version that applies to level fluid flow. P plus 1/2 rho v squared is equal to a constant. In this case, P is the pressure on the fluid at a particular point, rho is the density of the fluid, and v is the velocity or speed of the fluid. Thus, we can apply the expression to two different points along the flow path, since at both points energy conservation means the sum of the two terms must be equal to each other. Combined with the flow rate equation, one can use these to solve problems such as we solved problems involving conservation of momentum and conservation of energy. Chapter 10 opens the relationships between various temperature scales. Fahrenheit is the temperature scale we tend to use most often in everyday life, but Celsius and Kelvin are scales more used in the sciences. Some equations in this course not only work best in one of these two temperature scales, but can only be used correctly if the correct temperature scale is used. This can be a big stumbling block in problem solving. Since Chapter 1, it has been strongly suggested that one should include the units of numbers placed in the variables of an equation along with those numbers, manipulating those units as appropriate to make sure that the unit one arrives at matches the expectation of the variable being solved for can help in preventing that stumbling. Chapter 10 continues this emphasis on energy and energy conservation with the introduction of terms internal energy, heat, specific heat capacity, latent heat, and the first law of thermodynamics. Internal energy is a measure of the total energy of all particles, atoms, or molecules which make up a substance. This may include individual translational or rotational kinetic energies of the particles themselves, vibrational energies, both kinetic and potential, and a collection of other energy types that are individually hard to keep up with. Heat is all about the transfer of energy between parts. So it isn't energy in and of itself, but a means of energy transfer. Energy transfer in the mechanical world was explored in problems in which an object's potential energy was changed in lifting it from one point to another by some process, or changing its speed and thus its kinetic energy by some process. In the case of changing mechanical energy, we said work was involved. So work is an energy transfer process. Heat serves that same energy transfer purpose when it comes to thermal systems. Heat entering or leaving a system can either be related to a change in temperature the system undergoes or the change in phase, solid to liquid, liquid to gas, or reverse. Heat is not temperature, since temperature is used to tell the direction of heat flow. Heat flow can cause or be caused by a change in temperature, but not if the change is in a change in phase. In this case, the temperature remains constant. Tying this together is the first law of thermodynamics. This is the application of energy conservation to fluids. It says that the change in the internal energy, delta U, is equal to the sum of the work done on or by the system, W, and the heat added to or removed from the system, Q. It is necessary when considering changing the internal energy of the system to keep track of whether work is done on the system, which would increase the internal energy, or work is done by the system, which would decrease the internal energy. Likewise, heat flowing into a system can increase its internal energy, while flowing out will reduce it. Sign conventions are adopted to indicate these increases and decreases. Heat flow can come through three different energy transfer processes: radiation, convection, and conduction. Collectively, problems involving these concepts help address the competency, solve problems that involve thermal expansion, specific and latent heat, heat transfer, and the gas laws. Chapter 11 concludes the application of problems involving temperature and heat by introducing the concept of efficiency in machines and the concept of entropy. There are no perfect engines operating using heat, so efficiency is a means for determining just how well an engine performs, just how well it takes the energy it receives, QH, and turns it into useful work, W. That is, its efficiency is E is equal to W over QH. The second law of thermodynamics plays a role in identifying the most efficiency one can expect from a particular heat engine operating between two temperature extremes. This ideal heat engine is referred to as a Carnot engine, and it provides an upper limit to the efficiency of any heat engine, since that efficiency will always be less than the efficiency of a Carnot engine operating between these same two temperature extremes. In this case, the Carnot efficiency is equal to T hot minus T cold divided by T hot. So, for a heat engine operating between two temperature extremes, its efficiency, E, is always going to be less than the Carnot efficiency. The second law of thermodynamics was developed out of the work with heat engines. It states that no heat engine working in a continuous cycle can take the heat from a reservoir at a single temperature and convert that heat completely to work. That is to say, it is not possible to have an efficiency of 100%. It is the application of the second law to heat engines operating between two different temperature reservoirs that shows that the efficiency of such an engine must be less than that of an ideal Carnot engine operating between those same two temperatures. Similar conclusions can be drawn about refrigerators and heat pumps discussed in this chapter. Entropy is a measure of the disorder of a system. Like the change in internal energy that is covered in the first law of thermodynamics, it is the change in entropy of a system that is important, not the individual values of entropy in any one state. One form of the second law of thermodynamics states that the entropy of the universe never decreases. In other words, in a small region of the universe, one might see a bit less disorder. But if one then looks at the entropy of the whole, you will find more disorder than order, even on the largest scales. Entropy is not a conserved quantity like energy. Chapter 11 concludes by applying concepts of the first and second laws of thermodynamics to power plants, as well as commenting on the notion of perpetual motion machines. Power plants are essentially heat engines operating between temperature extremes. And because of entropy, it is not possible to construct machines proposed to put out more energy than is put into them, or construct machines that claim to get work directly from a heat energy removed from a single temperature source. In conclusion, though there are only two competencies addressed in these three chapters included in Module 3, they form the basis of much of the energy production around us. Cars, planes, trains, and power plants, to name a few, all operate within the framework of the first and second laws of thermodynamics. This course competencies provide the context in understanding these concepts.